one initial observation is that the distinction between thin and light is important here. If something's modelled as thin, it doesn't have any width, then that would seem to suggest that it doesn't have any mass either. But if the thing was massless and weightless, then it'd just float and there wouldn't be any friction at all, so we need to assign a weight to the frame. Now, the first thing to do is really try and vividly imagine how this triangle is going to sit on the peg, with the peg at various positions on BC. Okay, so I'll try to explain what's going on in this diagram. The whole question kind of hinges on this observation that the centre of mass is going to sit directly below the peg, whatever the position of the peg on BC. It's important not to confuse the centre of mass of a triangular lamina, which is the centroid, with the centre of mass of a triangular frame, which is what we have here. So for the time being, the distance from BC to the centre of mass is just defined as some unknown quantity y. Now, the way to formulate an argument here is to use some physical intuition and to consider what would happen with the peg at various positions on BC. How would the angle of the frame vary? So at the peg we have these two forces, the normal reaction and the friction. And just think about how those are going to vary as the frame becomes increasingly lopsided. With the peg in the centre of BC, the normal reaction force takes all of the weight of the frame, but as the frame becomes lopsided, the friction force at the peg takes an ever greater proportion of the weight, and so we need to consider the limit case when the peg is actually at vertex B. Now you might say, if the peg were at vertex B, then there wouldn't be any friction at all because it would be wedged in there. But remember, the peg can be arbitrarily close to the vertex B without actually being wedged in there, so it is the limit case that we need to consider. So that's the reason for defining these quantities in the diagram. We have x being the distance between vertex B and the peg, and the angle phi being the angle between the horizontal and the side BC. Now notice that the angle phi will be needed for expressing the components of the reaction and friction at the peg. We're going to be interested in these quantities in the limit case when the centre of mass is directly below the vertex B, and so that's why this angle gamma is useful. And finally, the reason for defining tan theta in terms of these two side lengths L and H is that we're probably going to get a result in terms of tan gamma, and the result we need is in terms of tan theta, so making that definition will allow us to relate tan gamma and tan theta. So what I've done on the next page is just to explain those definitions, and then to make a note of the main argument, which is that, as we said, the friction increases as the distance between the peg and the vertex decreases. And notice the range here of x being between 0 and L, whereas the length of BC is 2L, because by the symmetry of the triangle, if the argument holds for one half of the triangle, it must hold for the other half as well. So the plan is to find an expression for the friction as x approaches 0, and conclude that if it's less than mu times r, then equilibrium is possible, not only as x approaches 0, but for the peg being at any point on BC. Next then, we need to calculate the distance y between the side BC and the centre of mass. Now, since we have an angle and one side of a right triangle, we can get the other two sides in terms of those two quantities. So we have L cot theta for the adjacent side and L cosec theta for the hypotenuse. And in the equation for the centre of mass, we have on the left-hand side the total mass times the distance of the centre of mass from the side BC. And on the right-hand side, we have the individual masses of the sides times the distance of their centres of mass from the side BC. And that's just using the fact that the masses of the sides are proportional to the lengths of the sides. And also that the midpoint of the hypotenuse is going to be level with a point exactly halfway along the adjacent side. So that allows the value of y to be calculated. Here, s and c are just sine theta and cosine theta. And that last equality just goes back to the earlier work where we defined tan theta as L over h. Now, we're going to need an expression relating r and f. So a sensible thing to do seems to be to take moments about the centre of mass, because then we won't have to worry about the weight. And actually, because the centre of mass is directly below the peg, that amounts to the same thing as just resolving horizontally. Considering the horizontal components for equilibrium, then, we must have r sine phi being equal to f cosine phi. and f then being equal to r tan phi, which must be less than or equal to mu r. The next line is noting that as x approaches 0, the angle phi approaches pi over 2 minus gamma. And that can be seen just by considering these quantities in the limiting case when we have the centre of mass, which is labelled W here, being directly below the vertex at B. So in that case we have tan phi approaching tan pi over 2 minus gamma, which, using a standard trig identity, is equal to cot gamma, and that's the reciprocal of a quantity we defined earlier. So plugging in the value of y that we derived earlier, we find that we have this L over H term, and that's exactly how we defined tan theta earlier on. So this is the result that we're looking for. It says that in the limit as x approaches 0, tan phi approaches this 2 tan theta times 1 plus sine theta. Now, going back up to the result at the top right of that page, we have r tan phi being less than or equal to mu r, and r is just some positive quantity, so we can cancel that from both sides of the inequality, and we have tan phi being less than or equal to mu, and we've just found tan phi in terms of theta. So we can conclude then that mu being greater than or equal to this expression in terms of theta implies that the friction will not go beyond its limit for equilibrium even as x becomes arbitrarily small, and so with the peg at any point on BC, equilibrium will be possible.